Okay, and we're back. We're going to do some examples of probabilities of dying and probabilities of surviving. So from last time, we recall that NQX is the probability of dying in the N years after age X. And NPX is the probability of surviving N years after age X. And NPX equals 1 minus NQX. They're complements. So, for example, 5 Q20 is the probability of dying in the 5 years after age 20. So that is the probability of dying in the age interval 20 to 24, because this age interval is 5 years long. It goes from age 20 up to the end of age 24, so 24 and 364 days. Now, let's notice that if we have something like L0, which is our radix, then if we have L0, we could get 1P0. That's the probability of surviving in that next 1 year period. That would equal L1. That's the survivorship at age 1. L1 times 1P1, that should be equal to L2. That's the survivorship up to age 2. We can continue this, and we can see that L5, we can do the expansion just like we did before, and we can do a substitution. We can see that L5 should equal L0, our radix, times 1P0, times 1P1, times 1P2, times 1P3, times 1P4. There are 5 years, and there are 1, 2, 3, 4, 5 of these probabilities of surviving. These 1 year probabilities of surviving. So in general, for any age X from L0, that's going to be the product of the 1P I's from I equals 0 up to X minus 1. Let's point out one more thing here. Since NPX, the probability of surviving, is equal to 1 minus the probability of dying, that means that L5 should equal the radix L0 times 1 minus 1Q0 times 1 minus 1Q1 times 1 minus 1Q2. We've got 2 more terms, 1 minus 1Q3 and 1 minus 1Q4. And what do we see? What we see here is that the probabilities of surviving multiply in order to survive this cohort, this original cohort of L0, our radix, of L0 people up to L5. The probabilities of surviving multiply, so 1 minus the probabilities of dying equal 1 minus the probabilities of dying. So the probabilities of dying don't multiply, the probabilities of surviving multiply. You guys probably already know all of that. Let's ask a question. In this case, over the age interval from 0 to 5, so we're looking at L0 and L5. Let's ask a question. What is the average death probability? Let's say the average 1 year death probability. Wait a second. That looks kind of like if we'd written something that looked like K5 equals K0, 1 plus R0 times 1 plus R1 times 1 plus R2 times 1 plus R3 times 1 plus R4. And we know how to solve that. We know how to find the average growth rate R. We can find the average 1 year death probability in the same way. All we need to do is do exactly the same thing before. We can calculate it, and the average death probability, 1 year death probability, is going to be L5 equals L0 times 1Q, let's call that I, to the 5th. That's going to be the average one. So we already know how to do that, and now you can see why I did those silly calculations with the growth rate in that very first lecture. It's because later on we're going to see that we're going to use exactly the same technique to find the average growth rate for any 1 year period from a series of 5 year rates. And just like for the average growth rate, we did not need to know all of the individual growth rates. All we needed to know was the starting point, the ending point, and the number of years in between. In the same way, if we knew what L0 and L5 were, and we knew how many years in between, then we can calculate what that average single year death probability was. So let's do another related thing. Let's ask, what are person years? And we looked at this earlier, and we saw that in the Lexis diagram. Let's go back to that for a moment. Here's our Lexis diagram. We have a cohort of people. Some of them live for a long time. Some of them, unfortunately, die early. We have this. And now we have ages. And so let's have age, let's say 10 here and age 15 there. And so what we're going to do, if I did this right, we're going to count the number of person years lived by this cohort between the ages 10 and before their 15th birthday. So what we're going to do is we're going to add up the lengths of all of those lines and add them up, and that's going to give us the total number of person years lived. Well, we already actually remember how we created the LX curve. Now this is our L curve, and this is our age over here, before we had age over here. And what we did was we took each of those lines, we sorted them, and then we made them horizontal, so the short lines were up here, and then we calculated what that curve looked like that. And now if we were interested in the number of person years lived between age age 10 and 15, that's 10 and that's 15, we have all of these lines, some of them, because they were sorted, some of them were short and then they died there, and some of them were much longer. Some of them lived for quite a long while. And now if we're interested in the number of person years lived in a particular interval, what we're interested in is how many person years do all of these things add up to? Before we added up all the lengths of the lines, we could do the same thing here. We're going to add up all the lengths of the lines that this cohort experienced before they died. Some of them died way off to the right-hand side. Some of them up here died within this 10 to 15 year age interval. Fortunately, some of them lived long and happy lives, and they died out here. So you'll recognize that this area in yellow, that's just the area underneath this L of x curve. It turns out that we could calculate it, since we're only interested in this yellow part. The other way we could do that is to calculate these vertical strips. And that you'll recognize is just the integral, the area, the cohort, person years lived between ages x and x plus n is just going to be the integral from x to x plus n of L of y dy. This is so important, we give this thing a name, and that is going to be n capital Lx. That's what we mean by the number of person years lived, and now you can see why we use a capital L for this and why there's a lowercase, because often when we take the integral of things, then we use the capital letter, so we call that NLX. And let's go back here. That's this column that we're talking about. Where is it? Right there. We actually are going to come back in a minute. We have a conceptual way to do that, which is as this integral of the L of x curve. I guess what I should do is, because we're talking about a function, in that case I should be using my functional notation. I'm going to call that L, use that functional notation like this, and I should use this here so we know that's continuous. Let's see now. Where am I? Here I am. In a couple of minutes, we'll see several different ways to calculate NLX numerically, but the conceptual idea is that it is the number of person years lived in the n years following age x, and that's the area underneath this L of x curve. That's the area in yellow. But first, before I go into how we calculate it, we're going to talk about why we use it. As I said before, when we were talking about birth rates and death rates, our denominator is actually the numbers of person years at risk of exposure. So what we're going to introduce is the mortality rate, the age-specific mortality rate for a cohort. And what we're going to do is the mortality rate is going to be n little m x, and that thing is going to be the numbers of deaths in the n years after age x, so it's the number of deaths between age x and x plus n, and what's in the denominator, you've guessed it, it's going to be NLX. So that's going to be the number of deaths divided by the years of exposure, or the years at risk to dying. So in the numerator, we're always going to have the number of events, and then the denominator, we're going to have the exposure to that event. So in this case, we're looking at deaths. We could look at births. And so the numerator will be the number of births, and the denominator will be the years of exposure to having a birth. Okay? So just to recap, NQX is our probability of dying. That is NDX divided by L of X. It's a point. It tells us the number of people dying in the n years following age X, given the population at risk, which is L of X. And then we have NMX, which is our mortality rate. That's going to be NDX divided by NLX. And so that's going to be NDX divided by that integral of L of Y dy from age X to X plus N. And we'll come back to NMX later. Okay, so now that's where we want to get to. Let's talk about how do you calculate you know what? I think I'm going to stop right here, and we'll pick it up in another video. Okay.